So in the block diagram of the communication system, we discussed at the beginning of our previous chapter, right? We had a block called the source encoder, right? So source encoder is the one which performs what is called as a source coding. It's a process in which the output of an information source is converted into binary sequence. All right. So fundamental idea behind the source coding is, right, I might have to change the format in which the message is being generated. Right. Message maybe it contains ABCD, but ABCD may not be in the proper format in which I can send this message, right, on the channel. So what I have to perform is I need to convert this into another format. Okay. So let me quickly write this. So source coding, it is a process. It is a process of converting the output of our information source to binary sequences. Right. So basically, the job will be completed by a device called as the source encoder. So source encoder will be used to convert any given sequence into, right, any other given sequence, right? So that's what is this technique. Okay. So ultimately, I'm trying to convert a given sequence into any other format by the source encoder. Okay. So the first possible question would be, what are the various types of codes that can be, right, used? Type of codes or the, okay, let's look at the types of codes first. So it's a theory question. Types of codes that can be obtained by using source coding. So various types are there. We'll discuss 5 of them. The first one is what we call as, say, the block codes, right? So first technique is called as a block codes. Right. Block code is a specific type of code which maps each of the input symbol of the source alphabet into some finite sequences. Okay, so block codes will be, it's actually, it's very simplest format. Okay, so let me try to write the definition. We'll give an example as well. All right. So it is a code that maps each input symbol, each of the input symbol of the source alphabet let's try to denote the alphabet source as capital S. S contains all the possible what you call messages that get generated by the source, right? It can be ABCD 0011, etc., right? Anything. Source alphabet, everything that is generated in the source alphabet S into a finite sequence, a finite this as a finite sequence. Okay, let's see. Right. So normally from the code alphabet into the code word, right? So this normal conversion is defined in the following way, right? So let's try to write the S source as maybe S1, S2, S3, and S4. If this is the source, right? and the output, the possible symbols, let's say the X contains zeros and ones, right? The X contains the set of alphabets called, it's called as the code alphabet. Okay, it's called as a code alphabet because code will be generated by using these symbols, right? And the result of the coding is called as a code word, right? For example, maybe this is just an example. So the source alphabet, and I'm writing the code word, right? Maybe this is one of the case. So wherever I have S1, maybe I'll code it as a 0, 0. Okay, S1 can be coded as 0, 1. Say, okay, sorry, this is S2 and this is S3. Okay, S2 is 0, 1, S3 is 1, 0, and the S4 is, sorry, S4 is 1. Right, so you can see that, right, this is how the block codes are going to work, right? Every symbol in the source, everything in the source alphabet will be converted into, right, another code word. The code word gets generated basically from a set of symbols. We call them to be present in the code alphabet. So these are the terminologies we are going to use. Okay, I try to define everything here, right? So that is about the block code, right? So we'll move to the second type of the codes that we generate here in the source encoding. So the second type of the codes will be classified into what is called as a non-singular code. Non-singular code will be the second type of the code. Okay, so now we'll discuss about what is a non-singular code and how do you define this, how to justify this. Okay, it's again, right, it's a type of the block code. Okay, now any block code is said to be a non-singular code under certain circumstances. Okay, there's a special, it's a special case. So when you call it as a non-singular, right, if and only if all the code words are, right, present, right, distinguishable from each other. Okay, so each and everything, right, should be distinguishable. If at all I have the same source S and same X given here, right, the code word will be, we can say that it is a non-singular code only if the code words are distinct, right? Whenever we have a distinct types of code words possible, right, we will be calling them as the block code. Okay, for example, I'll write the statement first. So a block code is said to be singular if each code word is, we say that it is distinct. Okay, or you can try to distinguish them from each other. So as soon as that happens, you can say that yes, it is said to be the non-singular code, right? Let me try to give an example here. So we have the same S and same X, right? So the source symbols and the code word we generate, let's assume, okay, this is just an assumption as of now. We are not following any specific rule to convert a source into the code. So it's just an example. Okay, so we have S1, S2, S3, S4. So let me say that code for this is 0, right? Then my next one will be say 0, 0. then I go for 0 1, then maybe I'll use 1 1. Okay, so I can see that, right? I didn't start with the 0 0 directly. I started with a single element. Then maybe I'll use 1 as another element. But if I use simply 1, maybe I have a problem here, right? Identifying this one with the other one, because there is a single 0 already existing. Okay, so because of which maybe there is a confusion coming in the picture. So just to avoid that, we are using this kind of notations. Okay, right? It's just an example, right? We'll see how to generate each type of the codes using the rules later. Okay, we'll define the rules and we'll try to first we'll define the rules and then we'll get the codes for various types of what you call the messages. All right, that's going to come at a later stage. As of now, we are simply trying to distinguish. Okay, so the second type of code is said to be the non-singular code, right? Just remember this name. All right, then all right, let's move further. The third type of the code is said to be, okay, let's try to define it, uniquely decodable. Okay, let's try to define the third case, which is the uniquely decodable. Okay. This is the third type, that is uniquely decodable code. All right. Whenever we try to define the code, right, it is said to be uniquely decodable, or right, uniquely we can actually separable code if every code word present in a whatever received sequence can be uniquely identified, right? So we can call it as if the received whatever we say, if the received code word is uniquely identifiable, you can, right, identified. If at all I'm able to do that, then we call this kind of the codes used for generation will be as a uniquely decodable code, right? So uniquely decodable codes, let's try to write here. All right, so this is the example. So the symbols are say 0 0, right? Let me try to write in a slightly different way now. So okay, so the symbols which we want to send could be 0 0, 0 1, 1 0, 1 1. But you see, if I have, I will directly code this as 0, code the 0 1 as maybe 1 0. Now you see this is 1 1 0. You try to code the next symbol as 1 1 1. Right? So from the received one, I can actually clearly distinguish between the various samples. So because of this, right, it is said to be the uniquely decodable code. All right. Anyway, let's move further. The next is next type, that's the fourth one, is called as the instantaneous. It is instantaneous codes. Okay, so how do you define the instantaneous code? Whatever is uniquely decodable, it's said to be an instantaneous code if the end of any keyword can be determined without the interpretation of the succeeding symbol. In the sense, I don't want the succeeding symbols to decide, right, what is there and what is the last symbol. In order to decide the last symbols of the code word, I don't need the successive symbols. All right. So it's called as a prefix code. There is another name to this. It's called as prefix. Right. So what is the prefix code? Right. If, let me write, if the end of any keyword end of any keyword can be determined end of any keyword yeah, can be determined keyword can be determined without the interpretation of the succeeding symbols. All right. Okay. Then we have one more type that is called as it's a last type or last uh, what you call type. So let me write it. So this is like optimal. It's optimal code. All right. So what is an optimal code? The length of the code words assigned to the symbols are minimal, right? We have various lengths possible. In the sense, the length of each symbol is not unique. It's going to be different, all right? And we have assigned the minimum length for each of the symbols. That's why it is called as optimal. Okay. So I'll quickly write here, if the lengths of the code words assigned to the symbols are minimum, right? So with the minimum length, we try to assign various codes. So if that is the case, we will be calling it as the optimal code. Whatever code we obtained, right, we will call that as a optimum code. Okay, I hope it is clear. Right now, let's move on to what is called as the source coding theorem. It is the second uh, theory question that can appear, right? Also, this is used in various problems. All right, so source coding, source coding theorem. All right, now let us consider that there is a information source, right? And the information source generates the symbols SI from the source. Okay, so let me write quickly about this. I have a information source. Okay, and from the information source, I generate the symbols. So let's say that the symbols generated over here are denoted by say SI. So SI is the set of symbols being generated, and there is a source encoder performing the encoding operation. Okay, so once this encoding is done, we get an output. So the output of this is said to be, say, BI. SI gets converted into BI. All right. Source encoder is the one who generates this encoded information, that is BI. Okay. Now, so let us say that there is a length associated with each of the code word, right? That is generated by this. So I'll write that statement here. So I'll write Li. So Li be the length of Li be the length of the code word for, say, that is ith symbol. I have many symbols. It is ith symbol I'm talking about, right? So what is the average code word length, right? This implies the average code word so let me write the average code word length. So average code word length, that is capital L. L is equal to summation all the symbols, that is I is equal to 1 to n. See, this will be the probability of the ith symbol into the length of the ith symbol, pi into Li. I think it looks like B. I'll change. Yeah, Li is the length of the ith symbol. Okay, there are many symbols generated, right? Each one is of different lengths, right? So pi into Li over the summation gives you capital L. Okay, yes. Now this is the average length. Fine. But what, using this we can actually calculate what is called as the efficiency of this encoder. Okay, this is an encoding technique. So efficiency of the encoder, right? We can calculate, that is eta s is equal to the minimum length L minimum divided by this average length L into 100. Answer comes in percentage. Okay, now we'll move ahead. These kind of equations we are already familiar with. Now I'll go to the entropy. Now you see, information content, average information content of a message is conveyed by which one? What is the tool we use? It is entropy. Okay, right. So we can try to represent lesser bits than the entropy, right? So that means, you see, but we know this, right? So since, how I am writing this, I'm writing this because I know that entropy gives the average information conveyed by the source. Okay, no symbol emitted from the source can be represented with lesser bits than its entropy. Correct, we already know that. So also I'll simply write also. I'll not give any explanation because we already know this. This length, average length, will be more than or equal to h of s. Correct. So that means minimum value of L should be h of s. Correct. That means L minimum, whatever is the minimum length you want to represent, that should be equal to h of s. Right. This is actually the theorem which I was talking about. Right. So we gave a statement that source coding theorem says that the minimum length of a message that you can try to represent equal to the entropy of the message source, right? So since that is the case, I'll try to substitute. Therefore, this implies the efficiency eta s can be equal to L min is what? L min is h of s, correct? That is h of s divided by the average length into 100%. This is the equation we use, okay, later stage in problems. Also, I can calculate the redundancy if required. Redundancy, right? Normally we write R redundancy of the source, maybe, or okay, there was one term which is RS already used. So just to avoid, I'll write R eta. Okay, it's in terms of redundancy in terms of efficiency is equal to 1 minus eta s. So these are the various equations we will be using to calculate the required terms. Okay. Is this fine? Okay. Now, so we move on to the actual coding part, which is the Shannon's first encoding theorem. All right. So, right, we use a logic so that we can apply that to the problem, to the encoding problem, and we can get the encoded results. All right. So the theory part of that is what I'm going to call as the Shannon's first encoding theorem. Shannon's first encoding theorem. We will apply this. It's also called as, some of the authors or some textbooks, you may find a different name for this. Okay, this is said to be Shannon's encoding algorithm. Right? So what we do is we simply apply the following steps and we will calculate the required answers. Okay, so very simple method, right? We just have to calculate certain probabilities in our steps and we will simply get the result, okay, by using this method. And it's considered to be one of the efficient technique. All right. Okay. So our first objective is that we start with the problem and we have certain symbols given. Okay. And the symbols with certain probabilities are also given. Okay. So as soon as we get those details with us, we will always try to follow the following steps to get the result. Okay. Right. All right. Now, so these are the steps to be followed. So we'll start with the step number 1. So whenever uh, we have a problem with us, right? So in the first step, we always try to write arrange the probabilities in the non-increasing order corresponding to the symbols. Okay. So arrange the symbols given in the non-increasing orders of their probabilities. Okay, we have to do this. First step is always this. So in the sense, let's say we have some S values given, correct? So arrange the S in some order. Okay, S contains the source symbol, so not probability. I'll write in terms of S. You try to arrange them in the S, maybe S1, S2, S3 dot dot dot. I'll try to write it in this order, such a way that their probabilities, whenever I write P1, P2, P3 dot 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 like this, they have to be, it's not increasing order. It can be equal. P1 equal to P2, fine. But it should not increase. P1 should not be lesser than P2. Okay, so P1 greater than or equal to P2, then greater than or equal to P3, greater than or equal to the next one. This is the condition. Okay. Right. So that will be the step number 1. Okay. As soon as I finish this, I'll go to the step number 2. Okay. So in the step number 2, I'm trying to represent them in the following way. So what I do, I'll try to calculate a certain way like this. So this is step 2. So here compute the length. I have to compute the length of the keyword, whichever keyword I'm using, right, to that keyword, such a way that I have to do some calculation. The length Li should be greater than or equal to the log to the base 2 of the probability of that particular whatever keyword I'm using right now, right? So I have to, right, use this equation Li. I have to calculate. Okay, find the minimum value of Li such a way that Li is greater than or equal to log to the base 2 of 1 by Pi. Is it okay? That will be step number 2. I'll make you to understand, right, this step when we solve the problem. Then I'll go to the step number 3. Once you have this Li with you, right, we try to define the certain parameters from the probabilities. Okay, so define the parameters. So I'll just write the parameters. I'll explain how to do this later. So start with, say, maybe Q1, initial value of Q is my parameter, Qi is my parameter. So it will start with 0. Then the Q2 comes, right, which comes to be maybe P1, that is equal to Q1 plus P1. Okay, and I have my next term coming up, maybe Q3, which is equal to P1 plus P2. I can write it as Q2 plus P2 and so on. This will continue. Okay, so I'll demonstrate this as soon as we reach the problem. Okay, so you will see that the last number Qn plus 1 becoming equal to 1. This is a must condition. Okay, such that, right, when you add up everything, you will reach n, where capital N is the total number of symbols. So I'll note here, this is the n represents the total number of symbols. Okay, then we'll move to the next step. That is step number 4 of the Shannon's algorithm is that I have to expand the Qi obtained, every Qi, you can see that previous stages, Q1, Q2, Q3, Q4, etc., right? Every Qi in the binary format. Okay. In the binary format till Li number of places, right, are filled. Okay. I have to do this. Anyway, I'll show you that later. So that is step number 4. And last step, that is step number 5. So the 5th step is that number of whatever the decimal places in the binary representation of Qi, right, are the code words. Okay, so get the code words. Get the code words from the decimal places. From the decimal places, right, in the binary representation, from the binary representation of every Qi. Okay, so for a Si, your representation you can obtain from Qi. You don't take the Qi completely, only the decimal places are sufficient. Okay, so that's how we calculate. This is the standard procedure to be followed, right? If the question is in the theory part, explain that, then you can simply write these 5 steps, right? These are the 5 steps. Then you can give an example, right, to say that, okay, this is how we can perform the coding. All right, so let's quickly go to the problem. All right. So, right, so this is the first problem in the Shannon's coding algorithm. So perform the Shannon's source encoding for the source alphabet. They will give a source alphabet saying that, okay, machine generates A, B, C, D as its symbols, source symbols with a probability. Each one will have a probability like this. Okay, so that is 0 0.1, 0 0.2, 0 0.3, and 0 0.4. Right? So simply we are applying the procedure we mentioned earlier. So what is that? So I'll go for step number 1. It says that align them in the non-increasing order of the probability. So first let me write the probabilities in the required format. So non-increasing, so it should not increase. So now whatever is given in the increasing order, so I'll write 0 0.4, 0 0.3, 0 0.2, and 0 0.1. So corresponding to that, make the changes in S. So this becomes D, then we have C, then we have B and A. Very straightforward. Step number 1. Is it okay? Okay. Now, let's calculate the minimum length required. So that is step number 2. Right? I have to apply the minimum length of the ith symbol. Li should be greater than or equal to the log to the base 2 of 1 divided by pi. So pi's are given 0 0.4, 0 0.3, 0 0.2, 0 0.1. So first I am actually calculating for b now. Okay, so L1, right? L1 should be greater than or equal to log to the base 2 of 1 divided by 0 0.4. Can you calculate this and tell me? Okay, so when we solve, we get this to be equal to, this is 1.32. Now you see L1 should be greater than that and it is a length, right? So take L1 as 2 because length, right? Not 1.32. It will not work. 1.5 is also not going to work, right? You have to take a full number. So L1 is that. Similarly, calculate L2. L2 should be greater than or equal to log to the base 2 of 1 by 0 0.3. Right? Please calculate that. So L2 will be calculated. L3, I need to, it should be greater than or equal to log to the base 2 1 by 0 0.2, and L4 should be greater than or equal to log to the base 2 1 divided by 0 0.1. So this comes to be 1.73. Again, I'll make L2 as 2 itself. Okay. Then the next value is 2.32. So I'll make L3 as 3. Okay. This comes to be 3.32. We'll make L4 as 4. So now you see the length of my first symbol, when I code it, it should be 2. Length of the coded sequence for the second symbol C is also 2. But for the next two symbols, B will have length 3 and A will have length 4. This is what we come to know now. Okay, there are 4 symbols. Okay, that will be the step number 2, right? Then we'll go for the step 3. So in the step 3 of encoding, I am actually generating the parameters, as you remember, right? Always you start with the first parameter being equal to 0. Okay, fine. The next parameter, so Q2 will be, right? It's actually P1 plus Q1. Okay, P1, whatever I have, P1 plus Q1. So P1 is the probability of the first symbol, that is 0 0.4 plus the previous value 0. So that becomes equal to 0 0.4. Let's hold on to this. I'll move further. I'll go for Q3. Q3 is equal to Q2 previous value plus the next symbol, that is P2. So 0 0.4 plus 0 0.3, this becomes 0 0.7. Are you okay? Then go for the next symbol, Q4. Q4 is equal to Q3 plus P3, the third probability. Is it okay? All right. So that should be 0 0.7 plus 0 0.2. You have 0 0.9 coming. So Q5, now you see this is Qn plus 1. How much? Why? Because capital N is equal to 4. Fifth symbol, always we expect Q, this parameter should be equal to 1. So let's verify that. So as per this equation. This is Q4 plus P4, correct? Q4 is 0.9. P4 is probability of the last symbol, which is in the decreasing order, that is 0.1. So you get 1. Yes. So your calculation is fine. Now, what I want to represent each of these Q2, Q3, Q4, Q5, right? I want to represent them, not only just that, not starting from Q1. So all the symbols I want to represent in the binary. Okay, so that will be the step number 4, right? So represent Qi in binary. All right. So when I try to represent in binary, I should make sure that the length of my binary data should satisfy this condition. The Q1 should be of length 2. Q2 should be of length 2. Q3 is length 3. Q4 is length 4. This has to be satisfied. Okay, that's why we calculated the minimum length required to represent the symbol using this step number 2. I just have to refer to these numbers L1, L2, L3, L4 whenever I do the conversion. But the first one is very simple because it is 0, right? So 0 can be represented in any format, whether it is binary, hexadecimal, or anything, any decimal notation, right? It is going to be 0 only. So directly you can write the answer Q1 is equal to 0. In binary, this 0 to the base 10 I'll write, because what we have calculated is in the binary. That is also equal to 0.0. Any zeros you put, right? Any number of zeros you can put, right? That will be to the base 2, correct? But you see, the length we expect, what is the length we expect? Length expected is 2, and that length 2 should be after the decimal point. So you write 0.00 to the base 2. This is my answer. Remember, the length which we have specified is after the decimal place. Okay, length 2 which comes here. Okay, when we go to the other numbers, this becomes more clear. Let me say I have Q2. What is the value of Q2? Q2 is 0.4 and it is to the base 10. Correct? Now I need to convert this into the base 2 notation, isn't it? So how do you do that calculation? If you remember the conversion of decimal number, base 10 numbers into base 2 numbers, before the decimal place, you keep dividing, correct? You divide by 2. But after the decimal place, you multiply by 2. Okay, so this is how the calculation goes. I'll do the calculation over this side. So that is, I have say 0.4 given, you multiply that by 2. So when you do that, you get a 0.8. Is it okay? So when I write an answer after multiplication, whatever is your whole number, right, before the decimal place, that will go. Anyway, so 0.4 starts with a 0 point. So after multiplication, whatever you get here, that will go to this location. You see, I'm writing a 0 here because of this 0. If at all this was 1.8, I used to write 1 here. I am supposed to write 1 here. Okay, I'll show you this calculation immediately in the next step where I get a 1. Okay, so 0, I multiplied and I got a 0.8 as my answer, right? And that 0 went here, okay, in my answer. So next you take, if at all this is 1.8, 1 has already moved out, remaining is 0.8. That 0.8 I bring here and I multiply that by 2 once again. So that is, you see, this is 1.6. This 1 goes here now. So 1 has been moved out, right? You are going to use 0.6 now. 0.6 into 2 is 1.2. That 1 goes here, right? And proceed further. Like this, it keeps on going, right? But I just have to check how many digits I want, how many decimal places I want, right? If you see the length of my second symbol, right? L2 is also 2, correct? L2 is 2 means I don't have to proceed further. Anyway, I'll write this answer. This is to the base 2. But since I am not expecting the length more than 2, I'll truncate this to 0.01 to the base 2. Are you okay? Right. So you get familiarized with the procedure once we do few more problems. Okay, so Q3 is equal to, you can see that this is 0. Right, 7. The next answer, right, whatever Q1, Q2, Q3, Q4, I have to deal with them. Okay, those probabilities, right? So 0.7 is, again, this is to the base 10. So how should I proceed? I'll write the 0 point as usual. So start with 0.7. 0.7 into 2 is 1.4. I have 1 over there, so 1 comes here. Then 0.4, remove the 1 and remaining part you write. Okay, so 0.4 into 2 is 0.8. So that means a 0 goes to the next position. Then 0.8 into 2 is 1.6. So 1 goes over there. 0.6 into 2 is 1.2. So 1 goes there, right? I can expand this further, but I don't need all of them because my length required is only 3, right? So 0.101 to the base 2 is sufficient for. That is Q3, correct? Let me go to the next value, that is Q4, which is 0.9. 0.9 to the base 10, right? We'll convert. So I'll start with the 0 point. So 0.9 into 2 is 1.8. So we have 1 coming into picture. So this is 0.8 into 2, 1.6. It's a 1. Then we have 0.6 into 2. This is 1.2. Next number is also 1. Then we have 0.2 into 2, 0.4. So that will be a 0. Then we'll write 0.4 into 2 is 0.8. Next number is also 0. Like this, it extends to the base 2. Since the length required is only 4, let me write it in this way, 0.1110 to the base 2. Okay. All right. Now, what I'm supposed to do, I'm supposed to convert them into the code words, right? How do you take the code words? After the decimal place, whatever you have, that is the code word, correct? So this is your result, right? I'll write the symbol and the required code word according to this method. So I have D, then C, then we have D, then we have A. So corresponding code word, D should have length 4, so 1110. Is it okay? Oh, sorry. This is for A, right? Because that is the last keyword. So D is the first symbol. So whatever you got first is the answer for this, right? D has the minimum length, right? You can see that the length of D, L1 is 2. The length 2 for D and C. Then B and A will have 3 and 4. Okay. So I should be careful when I write. Okay. So Q1 is 0, 0. That is for D. D will have length 2 and the code word is 0, 0. Okay. Then let's go further. The second one is 0, 1. So the code word for B will be 101. We expect the length 3, and the A will have, right, 4 length 1110. So this is the final answer for this particular problem.